All right, and I think we're live, or at least close enough. All right. So, chapter 5 continuous random variable. So far, we have been dealing with a set of data which we can count. We can assign some values, and they're much more tangible. Coins, marbles, um, kids, right? Things we coin flips, flips. Um, so things like this have been going on, and a lot of the conversation with that was relatively easy, right? Binomial distribution. Once you got past that scary equation, and I appreciate you guys finding my jokes funny. Uh, there is a lot more out there. The problem we're running into is what happens if we deal with measurements rather than single pieces of data. What happens if we have a measurement? What happens if the number of possibilities isn't exactly defined well? For example, heights, right? Can we talk about height of people? No, we run into a little problem with that is because, well, how tall are you? If you're a grown up, right, then you're gonna say that your height is, well, in my case that's going to be 6 feet 4 inches. Yeah, I'm a tall guy, right? But is this really precise? I mean, if we think about it, 1 inch, where's the scale? 1 inch is about what? Much? I'll call that 1 inch, right? Oh, here, hang on. We have a ruler. Okay, I overblown it. 1 inch. Well, that is a lot of wiggle room, right? If you were getting asked about, how much you want to make money wise, and you say, hey, I want 1 inch of $100 bills every 2 weeks, right? This, there's a lot of wiggle room. Well, what happens if somebody takes $1 off or puts $1 extra? Will you be able to tell the difference? Right? When we have thick things like coins, right? It's very clear that there's one extra coin attached to it, right? Same with this way, even easier, right? Well, that's 2 coins with, right? 2 coins. But if we take something slightly smaller, right? There's a bunch of post-its here. All right, there's this many post-its. What happens if I take it off screen and I take off 1 or 2 or 0? How many did I take off? Can you tell? Okay, let's try it again. How many did I take off? Right? This, the measurement of this, right, of how many post-its are here, not the count, but the measurement of it, right, starts getting as precise as my measuring tool, right? If I have one of those engineering rulers with a lot more divisions on it, I don't know if you can see. Oh, no. Okay, come on. Either way, just trust me that there's a lot more grid lines on this than you would expect on an inch ruler, right? or even that. You have inches on one side, centimeters on the other. 1 inch is a lot, and you're going to be like, it's about this much, right? But if you take it more precise and more precise and more precise, eventually you can pull up a pair of calipers and be like, hey, there's the exact thickness of this, right? So what we are talking about in chapter 5 is what happens if our distributions deal with this kind of setup where there's a lot of data values available, right? And one way we can talk about this is, rather than talking about, the histograms we came to enjoy because we could very specifically assign some frequency to each one. What we are starting to talk about is some distribution, right, of x's. But what we are looking at here is frequencies of possibilities. So what we are calling this is, we're calling it a density function, right? So this is a density function, right? This describes where you will see most of the data, right? In this case, most of the data would end up somewhere here. And what is very important about it, what I was trying to illustrate with the post-its, is the definition we see on page 74. Is that if I decide that I'm gonna carve up, where's came down for it, all right? That no, that's seriously. I leave my desk for one day. All right. If I'm going to carve up this little section over here, call this x1 and x2, and I'm going to say that my x is somewhere between x1 and x2, right? I'm going to be looking at this little piece of area. What I'm saying is that if I was going to add the final point into this, either here, or not include it at all, or include it at one side or the other, all of those things would describe exactly the same area in my density function, right? And since we are trying to get this whole idea that area and probability go together, right? The probability of this, this, and this is the same. If wrapping your head around this abstract concept is difficult, think of it as a bag of rice. So imagine we take up one of them big bags of rice, and for people that think bags of rice are manageable, those 20 pounds bags are manageable, think about a tractor trailer, 18-wheeler full of rice. So for our example, I'm gonna just take a look at this big bag of rice, right? And in this whole bag of rice, I'm gonna take one grain and I'm gonna mark it blue. Just gonna, Sharpie it all blue. So far, you're with me. What happens if I take this one piece of rice and I toss it in there? Well, and I'm gonna mix it, shake it, whatever. What are the chances that you reaching in with a pair of tweezers are going to pick out this one blue grain of rice only? Think about it. Pause, consider it. And if you don't like 20 pounds because 20 pounds is too easy, make it an 18-wheeler. Like, make it a huge, insumizable, uncountable amount of rice. You toss in a grain of rice. Now, if you're really lucky, ta-dam, it works. But really, the probability of you picking this piece of rice out of this huge bag is 0. It's not exactly 0 because this whole system is countable, but if we made it huge enough to estimate or assume that it's uncountable, this probability of picking that single piece of rice is 0. On the other hand, if I asked you to divide this bag of rice into, say, 3 sections, 3 equal sections, and I told you to pick a section where the grain of rice would be in, what would be your probability of picking that section? Well, probability that, let's call it probability 1, probability 2, probability 3. Right? If those are equal in size, the probability in each one of those is equal, which means that your chances of picking that section with the blue grain of rice is 1/3 in each case. Right? And so we can start talking about this, right, as we're talking about this as a space or an area. Now, what happens if you line out all the grains of rice in a row and you decide that, hey, I'm going to shift 1 grain of rice either way. So here's an example of what I'm talking about. My very expensive bag of rice. Here is my blue piece. Not very visible, but alright. So what I'm going to do is I'm going to take my huge bag of rice and I'm going to divide it into 3 equal sections. Yeah, close enough, right? And so the probability that we are going to pick the section that has our blue stone is equally spread, right? Because we're talking about section. But the probability you're going to pick this special piece out of this whole section, well, it's close to impossible. I mean, again, we're picking at random, so close your eyes and just pick one up without feeling it, without inspecting it, just kind of bing bing, right? And if this is not daunting enough, here, right, picking one of those, right? So how do we think about it? Well, think about it the following way. Let's say in an arbitrary way, we align all of those pieces of rice or stone, or in this case, but in a row, right? And we count off or weigh off, right, about 1/3, and we say, hey, this right here, this is the stone that splits this whole section, right, into a piece. And what I'm saying, and what the equations at the bottom of page 74 say, right, what this is all about, is saying that it really doesn't matter if we do this or that, if we cut off here or cut off here. Why? Well, because again, can you tell the difference between this and this? This and that. This and this. By count. Again, there's a limited number of pieces here, but this whole idea goes that we can start talking about populations which we don't necessarily have to count, which means that we can deal with populations that are a lot larger, and we can talk about populations which talk about characteristics which are continuous rather than discrete. Right, let me put this away. I'm going to turn off the mic for a second. All right, now that we are done with this, so that's the big kind of concept we need to get used to. All right, so now let's talk about example one. Actually, before we get to example one, what's up with the hurricane? I mean, Douglas and I got like 19 warnings on my phone, and my alarm went off like 8 times, and this whole thing's supposed to be like this huge thing. I mean, honestly, I had angrier, longer, and more intense breakups than Douglas. But just saying, on the East Coast, when they promise a hurricane, we get a hurricane. Here, it was alright. I mean, I hope everybody is safe, and maybe I just got lucky because of where I live. So if you're on Big Island and somewhere close to it, I hope you didn't get flooded. But I didn't feel the strength. I was kind of excited to see some rain, but alright. Example one. Example one says a random variable x has the uniform distribution on an interval 0 to 1. Alright, so what a uniform distribution is? Well, uniform distribution means exactly that. It's a square, right? If you think about uniforms in the military, everybody looks the same. So what it looks like is, it looks like that. That's a uniform distribution, right? This is a normal, right? Distribution, normal curve. This is a uniform distribution. Just bam, bam. Everything is the same. And it's on an interval 0, 1. Well, what does it mean interval 0, 1? It means the x values are between 0 and 1. And if the density function f of x is 1, so we are saying that f of x is equals to 1 for x belonging to 0 to 1. This little symbol means belongs. We can write it just as well for x greater equal to 0 and x smaller equal to 1. So that means the same. And f of x equals to 0 for x belonging to all real numbers minus the interval 0, 1. Or, right, x does not belong to 0, 1. Or x is smaller, not equal, smaller than 0, and x is greater than 1. All those ways we can talk about. What it really means, it means that there's a box, because it's 0 up to, the function is 0 up to 0, then it's 1, right? So if we had an imaginary y-axis, that would be height of 1, and then at 1 it drops back to 0, and then you have this. So it's just a box. For all 600 purposes, is a box. And then it says find p of, so a is p of x, p of x greater than 0.75 equals the probability that x assumes a value greater than 75.75. All right, well, so again, we're back to this kind of cool concept where we want to say, hey, we want to talk about this, right? We are very comfortable with area. I mean, I understand geometry is not everybody's ballpark, but we are not talking about geometry. We are talking about a very simple kind of a, here, there's your geometry, right? Or if you prefer, here's my uniform distribution. Right, so what I can do with this, I can say, hey, there is a 0 right here, right? There's a 1 right here, there's a 0.5 here, there's 0.75 here, there's 0.25 here. Oh god, you cannot see that. Let's try it again. That's horrible as with this. Alright, let's try this. Inventions. Dun, dun, dun. Okay, let's recycle this. Alright. So here's our uniform distribution. And this uniform distribution has a 0 on this side, 1 on this side, and presumably a 0.5 somewhere in the middle. Right? So that's our uniform distribution. And what we are asked is what happens, what's the probability that x is going to be bigger than 0.75? Well, 0.75 presumably is somewhere here. And we are asking about what happens if x is bigger than this. Well, so we are asking about the probability. What happens if we take our bag of rice, we put our blue piece of rice somewhere, and now we're asking what's the probability we're going to if we select this piece, what's the probability that that blue piece of rice is going to be there? That's all it's asking. This is asking. Assume there's something special. What's the probability it's going to end up here rather than everywhere else? Well, let's see. I'm just going to I didn't have enough arts and crafts as a kid, so I'm making up for it. All right. So now I took my bag of rice, I separated it into 4 pieces, right? Each one of them size 0.25, so 0 to 0.25, 0.25 to 0.5, 0.5 to 0.75, and 0.75 to 1. I have my 3 pieces. So here's the question. What are the chances I have my eyes closed. What are the chances that after shuffling it, right, I'm gonna randomly, still my eyes closed, I'm gonna randomly pick the blue. That would be really cool if this was, no, that's not blue. But, right, what are the chances? Well, it's 1 out of 4. Right, so what we are looking at here, we're looking at the probability, right, of this area. We're looking for well, probability of this area, maybe differently. Probability of the random variable being here, right, in terms of area. Well, the area of this whole thing is 1, right? 1 times 1, which means that which matches the probability, which means that this little piece, right, is 1 times a quarter. 1 times 0.25, right, which is 1/4. So regardless if you think about this in terms of area this way or in terms of area this way, you're still going to get the same answer, and that's 0.25 or 1/4, right? Now, the reason why I'm spending so much time on example 1, which is for most of you is going to be a very obvious and very easy example, is because it's very important to kind of grasp this concept of area and space and kind of a density of this function, right? This allows us to do a lot of cool things because we are no longer concerned about little aspects, because a single x has that thickness, so it doesn't matter if that little smidget is here or here. Alright, so that's part A. Let's look at part B. Part B says find x smaller than 0.2. So part B is we're looking for probability that x is smaller equal to 0.2. Again, that equal doesn't do anything in this regard, because that's a single value, and single value is one out of many. So if we look at this, and again, here's our little box, right? Height 1, length 1, so area equal to 1, which means we can very easily assign it probability of 1. And we're looking at 0.2, which 0.5, 0.2 will be somewhere here. And we're looking at this. Well, the size of this is 1 by times 0.2. That would be the probability, which in our case is 1/5, right? And again, we could, using the old method, kind of split up into 5 pieces and do this shuffle thingy again. Alright, and then third one, probability that 0.4 is smaller than x, smaller than 0.7. We're looking at that. Okay, well, there's my box, and I'm looking at 0.4, 0.4, and 0.7. Again, when you start drawing those pictures, they don't have to be perfect. Artistic freedom is a big thing here, because what matters is that somewhere in the middle there's the 0.5, and everything else, is it 0.4 here? Should it have been closer, further? Just as long as it's legible, we're okay. So now let's look at it. So now we are curious about this box. Well, how big is this box? Well, this box has still a height of 1. And what's the width of it? Well, the width of it is 0.7 minus 0.4, right? It's the difference between those two values. So it's 1 times 0.3, so it's 0.3. So the probability equals to 0.3. Oh, look at that. They actually drew it for you too. How cute is that? All right. Again, I'm trying to solve this without looking at the solutions and not reading the book recently for chapter 5, just so I can give you another way to look at it. If mine matches the book, great, but if it doesn't, well, there's another way to think about problems. All right, example 2. I feel like we've been doing it forever. All right, example 2. A man arrives at a bus stop at random time, that is with no regards for the scheduled service, or he takes a bus in a state which has aloha time to catch the next bus. The bus runs every 30 minutes without fail. Okay, maybe not aloha. Hence, the next bus will come anytime during the next 30 minutes with evenly distributed probability, a uniform distribution. Find the probability that the bus will come within the next 10 minutes. Alright, so first of all, what it says is that somewhere between somewhere between 0 minutes from now, as in he steps into the bus stop, the bus arrives, right? To he had to wait 30 minutes for the bus to arrive. The bus can come at any time, and he doesn't know. He doesn't care about the clock. The bus will come at most 30 minutes apart, right? At most 30 minutes apart, but it will come at some point, right? You don't know when it's here. It should be between now and 30 minutes from now, but we don't know when. And the probability at any given time of the bus coming is equal, and thus the uniform distribution. And so the guy arrives at the bus stop, which is right here, and then we're asking what's the probability that the bus is going to come within 10 minutes. Well, within 10 minutes is right here, right? Again, what's the concept? The concept is that we are looking at this continuous random variable, because time is a continuous random variable, can be measured as a continuous random variable, right? And the precision of timing is based on how good your watch is. If you have one of them fancy hourglasses, more than the time measured is once every 10 minutes, 15 minutes, 3 minutes, right? If you have a big one, an hour, but that's good. If you have something, regular with a little second hand, you can get slightly more precise. On the other hand, you can also get just minutes and so on and so forth, which means that we are running into concept of how precise time is, right? If I ask you about your age, you're going to say, I'm 22, right? But you're really 22, 2 months, 2 weeks, 2 days, 2 hours, 2 minutes, 2 seconds, 2 milliseconds, 2 picoseconds, and so on and so forth. And depending on how precise you want to be, you can be that precise. And so we have this. Now, for us to use this whole area probability thing, okay, this is gone. For us to use this whole area probability thing, well, we know the probability cannot be bigger than 1, so it would be nice if we could force this whole thing to be 1. Well, let's see, the bottom has a range between 0 and 30. So what's the height has to be? Well, if area equals to 1 and area equals height times width, and our width is 30, right? Then 1 equals height times 30, so height equals 1/30. So this height right here is 1/30. Alright, so that's check. So question is, how big is this area? How big is the red area? Well, the red area has a height of 1/30 because it's uniform, so it doesn't change, and it has a width of 10, which is 1/3. Right, so the probability is about 33.33333%. Now, do we have to do this? No, but that's one way to look at it. The other way is to say, hey, this is a uniform distribution, so the height everywhere is the same, so let's look at the bottom, right? Because both expressions are going to have a height in it, so let's look at the bottom. And the bottom says, hey, it's 10 out of 30, right? The slice here is size 10 out of a total of 30. And again, 10 over 30 gives you 1/3. And so notation between 0 and the bus could have right here, x smaller equal to 10 is 1/3. I know, not very cool bus stops and whatnot, but I'm going to leave it. But there's a lot more things to it. Now on page 76, there's a really cool formula on the bottom. It's really cool. I'm going to write it out here. By God, do not try to memorize it. Do not try to write it down as to be used for things in this class. Just don't. But there's something really cool about it. And Alright, so that's the formula. And this formula is really cool. And I'm going to tell you why it's really cool, but you're going to have to wait. So for now, I'm just going to... And again, don't put it in your notes. Don't do it. Just don't, right? Don't make me go on a rant again. So I'm going to put it right here. So it's going to keep us company. But leave it be. It's here, and we're going to deal with it in a second. Page 77. Page 77 starts talking about well, how not to lie, not to tell the truth. Page 77 says, if you want to do this area probability thing for other things, not uniformly distributed things, but normally distributed things, which are most things in life, are not uniform. They are rather more normal than uniform. There are some exceptions. There are some things that behave uniformly, but overall, things have this kind of normal distribution, right? There's a couple small things, most of it in the middle, couple large things, right? Or short, medium, tall, or poor, medium and rich. Of course, incomes don't work very well in America. Wealth equality, not discrimination. Not there's a bunch of things that don't work. But overall, if you think about the height of your family, there's a couple of short people, there's a couple of tall people, and most of the family is somewhere in the middle. Right? And if we look at the distribution in your family and say the distribution in my family, well, the average is different, right? And then I have smaller standard deviation than your family, and this just becomes kind of difficult. And if we wanted to use this cool concept of area probability, which, let's face it, barring that this is math and geometry and statistics and oh my god kind of thing, this is not exactly difficult calculations. I mean, those things aren't exactly rocket science. So you can do this multiplication. I believe in you, right? But if we wanted to do this on that, wait for it, little drum roll, you would need to build one of those for each one of these. Because this function describes this curve. And honestly, I don't know about you, but I had to build one of those, and then if I wanted to talk about the area underneath it, well, you have to put a little integral here and do calc 2, and the whole thing just blows up out of the proportion. It gets really huge and really fun. I mean, if you like that level of masochistic self-punishment called calc 2 and calc 3 on statistics, like, go for it. But doing this for that, doing this for this, is borderline obnoxious, because you have to do it for every single one, right? Suddenly in your family you're going to include your second aunties, and in my family I'm going to include my great grandparents, and this whole thing shifts, and I'm going to have to redo this whole thing again. I mean, Uh, um, no. The answer is no. I mean, really cool and really useful if you actually want to deal with it, but no, it doesn't get us as much information as we would like for as little work as we would like. So, right? But again, the difference between means, right, and the difference between the standard deviations is causing a lot more problems, right? Mean, standard deviations, and the mean for this. Right. So how do we deal with this? Well, what we can do is we could very politely, you know, and with a little bit of encouragement and, you know, cherry and sugar on top, we could take all of those normal distributions and put them through a magical box. Magical, right? Magical box. And what we could spit out is we could spit out something called standard normal distribution. And we could get this standard normal distribution. And this would be kind of cool. Because regardless of if you have this one or this one to start with, you pull it through this magical box and you get this one. Now bound that this one has this kind of formula lying, you know, assigned to it and so on and so forth. But if we are forcing everything to look the same, we could make some cool little adjustments to it. Like, for example, we could guarantee that the area underneath this curve, from negative infinity, right, as it goes up and then down to positive infinity, the area is 1, which would guarantee this, right? It would solve our whole dilemma, is the area 1, and this whole height calculation here. We could say, hey, we want the mean to be equal to 0. Wouldn't it be awesome that if there was a 0 in the middle? So if something is smaller than the average, it just has a negative number to it. And if something is bigger than the average, it is positive, right? And if it's exactly on the average, it's 0. It would make a lot of sense. And then if you looked at chapter 3 and 4, we dealt with standard deviation, and standard deviation had the tendency to come out of from a square root, and you know those equations were a lot. The zoom on this is horrible. All right, sorry, I'm shaking it. All right, well, there is square roots everywhere, so it was like, you know, those numbers were never pretty. It never was like a 2. It was always a 1.172 or something. It's just, so it would be really cool if we could force it to be 1. I mean, if we are using this magic box to take a normal distribution and make it a standard normal distribution, how about we just make one that actually works, right? Think about it this way. If you could design, if you had the unlimited resources and you could design the ultimate, I don't know, desk, kitchen, right, life partner, kid, whatever, right, wouldn't you want to design something that would be useful always? And so this is kind of this idea of putting it there, right? And again, I'm going a little bit ahead, but this idea is that we can do it using something we already know. Using the function z-score, we can map this normal distribution and a standard normal distribution with these parameters. All right, so that's kind of cool. And there's an inkling of it on page 78, but we're going to get to it. So just, I'm going to keep this in mind. This is what's getting really cool about chapter 5. All right, example 3. I feel like the more videos I make, oh, 3, not 5, the more I talk. All right. So height of 25-year-old man is certain in a certain region has the mean. All right. So 6975 inches with a standard deviation of 2.59 inches. Okay. So we have a mean and we have a standard deviation. The heights are approximately normally distributed, which is important, because if it's not normally distributed, we run into problems. Does the height of randomly selected 25-year-old man is normal random variable with a mean this and standard deviation? Okay, sketch a qualitatively accurate graph of a density function of x. Find the probability that a randomly selected man is more than 69.75 inches tall. All right, well, accurate graph. Well, that calls for, well, hell, close enough. With a sigma of 2.59 and a mean of 69.75. All right, and now it's asking you find the probability a random selected 25-year-old is more than 69.75. Well, so we're looking at 69.75. So we're looking at more. So we're looking at this. Anybody want to take a wild guess? How big is this? Well, I don't know. This is thicker, this is thinner, it's all crooked. Professor, teach you, you don't know how to draw. I'm like, yeah, well, neither you do. But anyways, I'm really bad at talkback. So we have this thing, and it's like, how do I deal with this, right? If it was a box, I'm good on the box, but this, what's the definition of a mean? When we talked about means, what did we talk about? When we talk about means, well, expected value, average, right? But mean told us where the middle of the data was, right? The center of the data. Median told us the middle value, but mean told us where the middle of the weight is. And if it's normally distributed with like looking like this, well, where's the middle of it? Okay. Here it is. Here's my graph. Where's the middle of it? How would you find it? Again, I know this is easy and most of you are good and golden and you're not worried about, but visually, where's the middle of it? Here? Right about there? Right? All right. But if I was going to set it up like this, right, on a, put it on my desk vertically, what would this be? Well, this would be some kind of a that. Well, how do I know it's the middle of it? Well, there's the middle, right? So this is the middle of it. If this whole thing is 100% or 1, how big is this? How big is this one little piece? Right? Because again, what we're looking for is probability that x is greater then 69.75. So we're looking for this, all this. How big is this? If this whole thing is 1, how big is half of it? Right? About half. How big is half? How big is half of 1? %, right? Because the mean is right smack in the middle of the data set. All right. So that concludes 5.1. 5.2. Here it is. All right, so remember this. 5.2 starts talking about this a little bit. So, example 4. Example 4. Find the probability indicated where, as always, z denotes the standard normal variable. Okay, so we're looking for p, z smaller than 1.48. Teach, it's a z. I wasn't paying attention to what happened. Well, this happened. We took some function that had an x, right? And we moved it into some function which has a z on the bottom. We changed all this just so the shape here looks like that, so we can deal with this. Right? So this z is just saying, hey, we're talking about a standard normal distribution rather than a normal distribution. We had a normal, we turned an x into a z, right, using this fancy formula that we had, x minus mu divided by sigma, right? That was our z. We plugged in the x, we plugged in the mu, we plugged in the sigma, we got our z, and then we assigned the z somewhere on this. And so, in our case, I like to put the notch in the middle just so I know where the 0 is, so it's easier for me to draw. 1.48, say here, 1.48. And we're looking for area that is smaller. So we're looking for this area. Now, again, it says that for cases like this, you can use the appendix, chapter 12 appendix tables, which I attached to Piazza for you. But you can also look at the table packet, and we're going to take a look at that because I find my tables to be, well, better. So there's the table. Everybody found it? Cool. So what does this table do? Well, this table does the following. The table has couple aspects to it. It has a z-score written out in both the first row and the first column. The z-score up front has one decimal place and then has an extra decimal place here. So what this means is that this cell right here is for a z-score that is 0.00. Right? These two zeros come from there, and this 0 comes from here. And then this. And what's in here in the middle of it is the probability. So I'm going to switch over to the other screen. So now what we have here, right, is this table. There's your z-score and there's your probability, right? there's your z-score, there's your z-score right here. So for this probability is referring to a z-score of negative 3.40. 3.4. 1 is here, 3.4, 2 is here, and so on and so forth. And whoops, sorry, wrong. And so we have this whole thing like this. Now that's part one. Part two is most of the standard normal cumulative probability tables like this one refer to the probability to the left of the z-score, not to the right. Not why? Because you cannot have a probability for just a single z-score. You can have a probability to the left, to the right, between two z-scores, but you cannot have a probability for a single z-score. So if you look at our problems, right, there is the reason why this is happening like that. All right. So now, what our picture looks like? Well, our picture looks like this. This is positive, and this is more than half, right? Because right here, the middle here is, well, that's 0, right? So what we're going to look is, we're going to look at the next page. Oh, hang on. All right. So instead of looking at the negative numbers on this page, we're going to look at the next page. And there it is. Right? That looks more like our picture. Right? That looks much more like our picture. And now we're looking for 1.48. Well, 1.48 is right here. 1.4 and 8. For people that have hard time seeing numbers and making mistakes, I found that putting a printout and then putting a ruler on it helps. For example, one of the tables I have, because I have way too many tables in my life, looks like this. And because all of it is so freaking small, I end up doing this to it. And if you take a look, there's the number right here. 9.3. Right? Alright, enough of the dreadful zoom. Alright, that's about right. So let's look at the other table. Bam. And shift the mic. And so what we have? 1.48, and there's the number. 0.9306. I'm gonna write it down. 0.09306. And question is, why is there discrepancy? So we can clearly see that this is the number right here, 0.306. So the question is, where do I get 0.9319? Here, I skipped a column. Okay. And again, you're going to make mistakes like this. So if you do, don't worry about it. Nobody's going to fry you for it. But be careful, because again, I just made a mistake like this on the screen, right, using this table. And again, this is the smallest numbers I could find on a table, and again, if I look at carefully, yeah, it should have been 0.9306. I wrote 0.9319. Why? I got shifted over by one. Right. So those mistakes will happen. You just have to be very careful. Again, why are we using this table? Well, we're using this table so we don't have to do this, because somebody was bored enough to figure that one out. All right, so again, this is the z-score that we're looking for. That's the z-score. That's the area that we want to. Why is this shaking? That's the area we're looking for, right? And this is the probability for the shaded region. And all because we could have done this. I think this is pretty cool, but that's just. All right, let's look at question B, or example B. We're looking for probability that the z-score is smaller than 0.25, negative. All right, well, let's draw it. Just a heads up, from my limited experience, students that don't draw pictures are about 60% more likely to make mistakes. So pretty please, with sugar on top, and a cherry, and syrup, and sprinkles. Draw the freaking picture. Takes you half a second. So we're looking at this little section right here. All right, so let's go back. No, not this one. No. Oh, here it is. All right, and this looks like hours, and we're looking for 0.25, negative 0.25. Oh, so let's scroll down. 0.25. Which column is 5? 5 is this column right here. So scrolling. This is the 5 column, and that would be this number. 0.4013. So 0.4013, and that's the probability for this area. Now I forced myself to always write z-scores below the axis and probabilities above. This way I won't make a mistake, because either this cannot be probability, this cannot be probability, but if you have two numbers that are small fractions, positive for small fractions, there could be a mistake made. So alright, let's see where we are at. Cool. Alright, next one. Example 5. I feel like I should be giving out swag or something for people that listen to me yapper on it. Find PZ greater than 1.60 and PZ greater than what am I writing? And PZ greater than negative 1.02. Alright, well, that's 0, so 1.6 say here, 1.6, and we're looking for things that are greater. Ta-dam. And so if we look up our table, I'm assuming you guys are good on looking things up on the table. Actually, hang on. I look at it on the table and it's the shaded area is in the wrong place. Maybe the other table is better. Hang on, what's going on? Huh, that doesn't look like ours. Ours is 1.6. So ours is the next page. Okay, so this looks more like our page. But hang on. Shaded on the left. Shaded on the right. What's going on? Well, okay, so I don't know what to do, so I'm gonna just follow things. I'm gonna shade this little area right here. Excuse me. Oh, sorry about that. I had to sneeze. So I shaded the area this, so it matches this. Now again, in a couple problems, you're just going to be fluently moving through it. Right now we're doing training, so yes. So let's look at 1.6. 1.6 is right here. 9452. So this area is 9452. So if this area is 9.52, what is this area like? Well, remember this. We forced this whole thing to have an area of 1, which means we forced this whole thing to be 1. So if this whole thing is 1, this whole thing is 1, how big is this black area? Well, the black area equals to 1 minus whatever came out here. Right? If this whole thing is 1, how big is this piece? Right? Right? If there's 10 stones total here, right? And this side is 7 stones, how big is this? There's 10 stones, so how much is underneath my arm? 3, right? If there's 10 stones total, and there's 9 stones here, how many stones are underneath my hand? Right? 1. This is not a magic trick. This is just addition, right? And so what we get here is that the probability for this section, for probability of z greater than 1.6, is equal to this. So that's 84500, 5.5%. And again, how do we do that? Well, what we did is we looked at the complement of this, right? They're mutually exclusive. You're in or you're out. So if this whole thing is 1, this is 9452, then this has to be 0.0548. All right, let's look at the next one. Let's try to do this one without cheating and using me as leverage. So negative 1.02, and we're looking for area that is bigger. So we're looking for this. That's 0. So if we look up at our table, and again you have plenty of tables to choose from, if you look up negative 1.02, I get 8461. Which means that this area is 1 minus 0.8461. Which means that the probability that z is greater than negative 1.2 is equal to that. And that's 92510. 523. 9351, yeah. All right, so there's there's this piece. Now let's talk about something cool that we can do about this. I'm going to put this right here so we can compare. Let's look at this. What would happen if we were to say look for this area right here, the mirror image of that. Well, if we looked up this area on our table, negative 1.6, I would get 0.0548. Again, here's the proof that I'm not cheating. There's my 0.0548 right there. Right? Well, that's curious. Why is that happening? Why is my number here and my number here exactly the same? Well, it comes from the fact that when we talk about a normal distribution, we're talking about a bell shape, symmetric. We're talking about bell-shaped symmetric curve. This is symmetric, which means that things that are bigger than 1.6 are the same thing as smaller than negative 1.6. Now, one has to be very careful with this information, because if you decide to start flipping things around and you make a mistake somewhere, you run into, like, those two things are equal, but you change any one of those, you put a minus in the wrong spot, you flip the sign in the wrong places, and the whole thing goes out the window, right? But this is something cool that one should be aware of, because some of the problems you can just look up. Sometimes you don't get a fancy table that holds both negative and positive sides, like 2 pages. You just get 1 page, and you should be able to work with it. How do you work with it? Well, if we're talking about this area, we can also be talking about this area, and that works for both of those, right? Hell, it works even for these as well, just because our cumulative standard normal distribution tables give you the probability to the left of the z-score. That just doesn't make sense to use it for these examples, but it does make sense to use for these. So if you're feeling very fluent and you're feeling very good, there's a way to think about it. All right, so that was example 5. All right, let's see how much. I think we have 18 examples in this. So, example 6. Find the probability. All right. I promise I'm gonna speed up a little bit, so if you want to watch the whole thing, that you don't feel like you lost most of your life doing so. All right. So, first things first. I marked 0 because of the way we have set up. Where's my setup page? Because of how we set up our little thing, the middle is 0. The middle isn't half, right? And this half doesn't refer to probability, it refers to a z-score. It's a 0.5 z-score. So what we're looking for is something that's 0.5, which is to the right of 0, and 1.57. And again, artistic freedom where you want to put those. Put them in such a place it makes sense for you and it's very visible of what you're doing. And so here we run into our first problem. The first problem we're running into is our table, right? If you remember, only gives us the probability to the left of the z-score. It doesn't give us probability between two numbers. Now you can Google a normal distribution calculator or a z-score calculator or a z-score probability calculator and find something that does this for you. Again, remember that in our case mean is equal to 0, standard deviation equals to 1, and those will be your x's, or in this case z's. But we don't have this. What we do have is we can find the probability for this. So we can find probability for z smaller than 0.5, which is this area right here. And if we look that up, 0.5, 0.5, 0.5, 0.5, we get 6915. So the probability here is 0.6915. That's one. So we got this blue area covered. That's this. And what we can find is we can take the green marker and we can say, hey, I want to find this area, this huge area. And again, we're looking at 1.57, and I get 9418. And that's for probability for a z-score smaller than 1.57. Alright, so we have this whole piece right here, all of that. And what we are interested in this area between those two pieces. So we take the bigger piece minus the smaller piece. And what this will give us is going to give us this space right here. It's going to give us this difference between this piece and this piece, right? You have this piece, take away this piece. If you want to see right? If you're going to measure how big this is, well, we're going to attach this part of the ruler at negative infinity, right? Measure up to here, and there's the number right here. So we don't need this piece. Right? So we have that, and then we're going to measure up to this piece, right? And the difference between how long this is and how long this is, right, is this piece right here. And this way we can go chop. And there is our piece, and that's right here, this. And that comes out to be 30520 about. So 25%, 0.03. Okay, let's try the next one. Probability that negative 2.55 is smaller than z, smaller than 0.09. Oh, quick note, if you use a fancy calculator to do those calculations, you will get a lot more decimal places, which means that the rounding might be slightly different. So your answers might be a little different. If they're a little different, and I mean a little different, they're still acceptable. If the answer starts being wildly different, you get a 24.7 here, that's wrong, right? So mind you that if your answers look a little different, you should be okay. And so we graph this, and 0.09 here, negative 2.55 here, and we're looking for this area. So just like before, we're going to look for this probability first, and negative 255, it's 0.0054, and probability here. Remember, probability has to be positive, so if you start putting negatives here, you're doing it wrong. And then 0.09, 0.09, 5359, 0.5359. So the probability for this piece, right, equals to 0.5359 minus 0.0054. All right, so that becomes 5035. There's your answer. And that was part B of example 6. All right, example 7. Let's see what example 7. What they sign up for doing. All right, probability for 1.13 smaller than z smaller than 416. All right, so here's the cool thing. If you look at this table, it's negative 349 and positive 349 are the most outside. If you look at the table we had here, it goes from 0 to 349. And if you look at the next page, or the previous page, it goes all the way up to negative 3.49. And look how small this number is. Right? Both of those numbers, this is almost 0, and this is almost 1. So depending on which textbook you get, most textbooks say that if you get to above 3.5, to assume it's about 1. If you go below 3.5, so if probability for z-score greater than 3.5, that's about 1. Probability for z-score smaller than negative 3.5, it's about 0. What we are saying here is that if we have this, and put a 3.5 here and negative 3.5 here, saying that this area and this area are really small. They're about 0. They're not exactly 0. And there's a way to calculate exactly how it is. So when you see this, what you should be thinking is that this is way out here, which means all this area is covered. So if we graph this, and we go from 416 to 1.13, and we're looking for this area. If we look up this area right here, 1.13, I got 8708. And how big is this area? Well, this area right here is about 0, which means that this area is about 1. Right? As far as our decimal places are concerned, this is 1.000. Right? It does not necessarily mean it's equal to 1, because this implies that there's zeros up to infinity, and here we're implying that our measurement goes only 4 decimal places behind. So there's this, but this is about 1, which means that the probability for that equals 1 minus equals 1 minus 0.8708, which comes out to be 2921, and that's our answer. Right? So if you have things like this, when you start seeing large numbers, means that it's very unlikely anything is happening above, or it's almost certain happening below. Or if you look at example part B, where probability is between -5.22 smaller than z smaller than 2.15, and we're looking for this area. Smaller than this, 0. What we are concerned is this section. And this section 215 is 0.9842. Minus this little section, but this little section right here, this right here, it's about 0. Why? Because this is such a big z-score. There are so many standard deviations away, right? Z-score describes a data value, how many standard deviations it is away from the mean. This is 5 standard deviations away. That's very small, very unlikely for happening. So we assume it's 0, and there's the answer. So when you see large, or super large, or super small numbers, just bear that in mind. So that was 7. Let's keep going. 8. 8 is cool. 8 is cool. Example 8 is cool because example 8 gives us the basis for the empirical rule, the rule of thumb. So first one says probability between -1 z1. So what it says is within 1 standard deviations away from the mean. And that's really freaking cool. Okay, well, we can draw this. Always draw. And if you don't do it on the main paper, do it on side paper, but always draw. Chances of you making mistakes are much smaller this way. All right, negative 1. Negative 1 gives us this area and gives us the area of 1587. Then 1 gives us this area, and that's 8413. 084, right? So the probability of those things together, I'm getting lazy here, 0.8413 minus 0.1587. So this error comes out to be 68.26%. Cool, right? We said that the empirical rule said that between -1 and 1 standard deviations away from the mean on a normal distribution, you get about 68% of the data. Well, there's here 68% of the data. If we do that for -2 to 2, what you should get is -2 is right here, so that's actually, let's do the +2 first. The +2 is 0.9772 minus 0.0228, right? And again, the picture for that would be, let's put it over here, -2, 2, we're looking for this. This probability is coming from this number, and this is coming from this number. And that should come out to be 0.9544. And again, 95%. And then the last one is probability of -3 smaller than z smaller than 3. If we look up probability for 3, that's 0.9987. If we look up probability for -3, that's 0.0013. And so this is 0.9987 minus 0.0013, and that comes out to be 0.9974. 99.7%. That's pretty cool. I think that's pretty cool. All right, so that's example 8. All right, 5.3. Actually, if you guys could you excuse me for a second? Somebody wants my attention. And I'm back. Now I'm happy to report my wife made a whole rack of ribs, barbecue ribs, and carrots, and baked potatoes, and homemade coleslaw. Oh God. And I'm here with you guys, so I hope you appreciate the sacrifices I'm making, because her cooking is to die for, literally to die for. You know the saying, I would stab somebody to get her cooking? Yeah, that's exactly that. All right. 5.3. In 5.3, I'm thinking about the ribs. In 5.3, we are starting to talk about the expansion of it. Because here, right now, we are comparing z-score to z-score. And we are comparing just that standard normal variable rather than the actual variable that we want to deal with. So in 5.3, we're starting to expand on this. We are starting to talk about the conversion from some x to some z and then to some probability. Of course, we're talking about an interval of x, which gives us an interval of z, which gives us a set of properties that we can calculate a probability, but this is the general concept we want to talk about. And so let's look at example 9. The example 9 says, hey, we have a mean of 10, a standard deviation of 2.5, and we are looking for p x smaller than 14. So step 1, we have the x, we have the interval for x. Now we need to convert it into an interval for z. So let's calculate the z-score. The z-score for this x is x minus mu divided by sigma, which in our case is going to be 14. I know this says x is smaller than 14, but if you remember our conversation about the one blue grain of rice, that still applies. So if it's equal or smaller than the same thing, so 14 is the border value, right? Either including the 14 or not, but this is the border value. Minus 10 divided by 2.5. So that comes out to be 4 divided by 2.5, and that comes out to be 1, 2.5. 4 divided by 2.5, that comes out to be 1.6. And so what we're looking for is we're looking for p where the z is smaller than 1.6. Standard normal distribution, which means we're looking at the z-score, so 1.6, and we're looking for smaller, so we're looking for that. And if we look up the probability for that, 0.9452, and that's the answer. Alright, let's look at B. Probability for x being between 8 and 14. Alright, in this case we have two values we need to convert to z-score. So z-score is x minus mu divided by sigma. Again, the reason why I write it is so I don't make a mistake. And that's 8 minus 10 divided by 2.5. So that's negative 2 divided by 2.5. So that comes out to be negative 0.8. And then the second z-score is 14 minus 10 divided by 2.5, and that comes out be 1.6. And so if we graph it, oh, somebody's making noise outside. negative 0.8 to 1.6, and we're looking for this area. We know how big this area is. We just calculated, right? So this is the same thing. And if we look at negative 0.8, that this area comes out to be 0.2119. Okay. Yeah. And so this total area is the big piece minus the small piece, and that's 0.7333. Again, if you do small piece minus the big piece, you're gonna get a negative probability, which is impossible, so should have been avoided. All right. Example 10. Lifetime of a thread of a certain automobile tire are normally distributed, blah blah blah. So this is example 10, and first thing is we have the mean with a standard deviation. Find the probability that the tire will be 1, 2, 3. That. All right. So there is two things here. One is we can solve this the regular way, and what we get is 2, 3, 4 minus 37512 divided by 4512. This, and very quickly you can realize that all of those have a lot of zeros. So one of the ways one can think about it is if I divide by 1,000, this becomes this becomes that, this becomes this, and this becomes that. Right? If you divide by 1,000, all of those numbers become much more doable. And since we are only doing basic math, division and addition and subtraction, this will work. So if we do it the same answer will come up if you use the simplification or not. So if you talk about thousands of miles versus just miles. But either way, you do this, and what do you get? You get negative 1.67. That's my first z-score. Now, here's the important part. When you plug this into your calculator, so 30,000 minus 3750, 500. If you plug it into the calculator, you ought to push enter first before you divide, and then divide. Because if you just keep on typing this minus this divide by this, what you're going to get is this minus this divide by this done first. Calculators, like, they should do division before subtraction, so you have to be careful. Why do I round to 2 decimal places? Because our table only gives z-scores in 2 decimal places. Right, so that's my z-score number 1. Z-score number 2 is 40 minus 37.5. And that comes out to be 0.56. So this area, negative 1, 7, 0.0475 0.0475, and then the big one right here, 0.7123. 0.123. And so what we get the probability for 6648. Oh, cool. So if you look at page 86, the cool thing that they did is they gave you both the x-axis and the z-axis. So they gave you the x values on one and they give you the z values on the other. The downside of that is it's prone to make mistakes. So what I would do is once you convert into a z-score, go with the z-score till the end, and then if you need to convert it back, but don't graph x normal distributions for x and then z on the same graph. Just do a z graph and you're going to be okay. It's I've seen it done before, and every time somebody follows a book like this, almost everybody gets a problem. So you do what you think, but healthy way is to, once you convert everything into a z's, just use z's till the end. All right, example 11. All right, this is a large example. Standardized score, college entrance exams. Aren't we all in college already? Right, mean 510, and this is example 11. Standard deviation of 60. Standard deviation of 60. Selective university score over, so we're looking for x's over 650. Find the percentage of all individuals who took the, all right, so percentage, proportion, probability, all of those talk about a fraction of something out of something, right? Proportion of black stones to all the stones, 1 out of 5. Percentage of black stones in this setup, 1 out of 5. Probability of picking a black stone out of all the stones, 1 out of 5. So that's when we see this, we know that we're probably talking about probability calculation. But again, percentage, proportion, all of those give the same things. So again, z, they're usually normally distributed. Alright, so z score equals x minus mu divided by sigma. So in our case, that's 650 minus 510 divided by 60, which comes out to be 650 minus 510 divided by 60, 2.33. And we're looking for the area bigger than. Alright, so the probability here for 2.33 is 2.33 is 99.01, which means that this area here is 0.0099, which means that the probability for z greater than 2.3, which 2.33, which is px greater than 650. Again, this is the same thing. This is what the value we're looking for. This is the representation in a standard normal form. Is 0.0099. So 1%. Alright, that's this. So that was example 11. Areas of tail of a distribution. Alright, so let's do an example and then I'm gonna talk about while I sort this out. Let's have something on paper, because the description is neat and useful, but I found that seeing is better. So example 12. Example 12 says find the z star of a z as determined by figure 510. Alright, so let's put the figure 520. 520 looks like this. So that's the figure. And it says find this value that cut off to the left. So we're looking at this. So what we're looking for is P of z smaller than z star is equal to 0.0125. Again, so what is this thing saying? What is this thing saying is we want to go from probability into a z-score and possibly later into the x value. So we want to do is we want to work that whole thing, we've been doing it backwards by having probability. And so that's relatively easy to do. What we need to do is we need to find this so we can find that. So we need to find this. Where do we look for it? Not on the edge, but in the midi part of the table. So let me pull up the big table. Bam. And let's see what we can come up with. So we're looking at 0.012. So it's probably not on this one. 0.00. How many zeros are there? 0.10. 0.0125. Oh, look, it's right there. I'm just gonna put it more in the middle of it. 0.0125. It's right here. It's right in the middle. I'm gonna shake the mouse right here. Right? Again, I'm not looking for 0.0125 on the outside. I'm looking at for the middle. Why? Because it says the probability equals to that, right? Probability equals to that, which means that in our case, we're looking at in the midi part of the table. So it's right here, right? The picture is kind of nice, but we're looking for an area to the left of it. And that's what? A z-score of -2.24. negative 2.24. So what it is it telling me? It's telling me that we would get this probability if we looked up negative 2.24 as a z-score. Which means that in our case, and if you decide to do it backwards, go from here back, you should be getting this. Right? Again, probability into a z-score and maybe possibly in the future to a value. It's not very difficult as long as you remember what you're looking at. In questions like this, I'm looking for this value. Right? You have one, you're looking for the other, and that's it. All right, question 13. All right, sorry, not question. Example 13. All right, example 13. Find the z star of z as determined by figure dum dum dum. All right, so again the picture. That's a 0. There's some z star here, and it's telling us this area is 0.025. Oh, how nice! They even told us that this area right here is 0.9750. How nice of them! And so what we're looking for is z greater than z star, and that equals to 0.025. So we're looking for a standard score such that probability of finding it above this is 2.5%. All right, so now that we have this number right here, that thing gets a lot easier. So we're gonna pop in our table, and we're gonna scroll to the next page, and we're looking for 0.975. 0.975, 0.975. Oh, look, it's right here. So that's 1.96, right? 1.96, right there. Oops. 1.96 right here. All right, so we look up back. So if this is, oh, sorry, I knocked it off out of bounds. So if this is 1.96, then the answer is that z is greater than 1.96, and that gives you 0.025. All right. So here's the part. Is this kind of area on one or the other side sometimes is referred to as a tail. This is a left tail and a right tail. And tails are used for us to talk about those small probabilities that are away from the average. Here, this is the smaller than the average. Here, things that are larger than the average, right? Probability is somebody is super tall, some probability is somebody is super small, kind of approach. So if we look at a general definition on page 90 or 89, so what we're looking for is 89, 90, bottom of 89, beginning of 90, is we are looking at this kind of setup. It's not the prettiest graph ever, but all right. What we're looking for is this symmetric graph where we have negative z and z. These are the critical values on left and right side, right? And this area right here is size C, and this area is size C, right? And this is how we define. This is a two-tail system, where this will be a left tail and a right tail system. So that's it for now. So let's look at example 14. Find z. Okay, so what we're looking for is z 0.01 and z 0.0 and negative 0, 0.1. So what we're looking for is we're looking for two symmetrical values, negative z 0.01, saying that this area right here is 0.01, and I have a second z here, 0.01, with this area being 0.01. Alright, for completion, how big is the middle part? Well, the whole thing has to be 1, so the middle part has to be 0.98. Alright, so let's look up this first one, because once we have one of them, it's symmetric, right? So once we have this, we can find the other one. So let's look up this one, 0.01. Alright, so I'm gonna come over here, look up our table. Oh, here it is. And we're looking for 0.01, 0.01, 0.01, 0.01, 0.8, 0.01, right here. Well, TH, I don't have 0.01, I have 0.0102 and 0.009. And I tell you, take the closer one. Which one's closer? This one, 0.099, is closer to 0.01 than this one. This one is 2 units away, this one's 1, right? This one is closer. So what value is that? It's negative 233. So this is the number we're looking at. Alright, so we have our value, and that's negative 0.233. This is symmetric, so this has to be 2.33. Or, if you prefer, you can look up all this area. And all this area is 0.99. So if we look up 0.99, what do we get? Let's see. Let's scroll over here. We probably need the second table. 0.99, 0.99, 0.99, 0.9, right here. And what is this referring to? This is 2.3, and let's scroll up. This is this column, this column, this column, this column, and that's 3. Here it is. 2.33 gives us 0.9901, which is the closest one. Which is exactly what we have here. All right. Cool. All right, next thing. So when we started talking about probability going into a z-score, and I said possibly this going into an x value, this is exactly what we are hitting on page 91. And on page 91, you're introduced to this formula. Now, the formula that I provided you in the book is this one. What it means is that if you want to convert from if you want to go from a z-score to an x, this is the formula you use. If you want to go from x to a z-score, the formula you use is this one. And you can get from here to here with using basic algebra conversion. Right? So what this is telling me is that if I have a probability and then I can find a z-score, I can get an x given that I have some mean and some standard deviation. So let's look at example 15. Alright, and it says find x star. By the way, guys, if you think you need an extra day on a homework for this, just let me know, because I know this is a lot of information. I've been getting some quick messages being like, hey, teach, I might need some more time. So if you need an extra day, just let me know. I'll extend the one of the deadlines out. So we're saying find x bar such, sorry, x star such that p x smaller than x star equals to 0.9332. So this is our main thing, and we know that there's a normal distribution, and with a mean of 10 and, excuse me, I think there's a mosquito caught in my water glass. And now there's a drowned mosquito in my water glass. Alright, so mean of 10 and a standard deviation of 2.5. Okay, how do we do it? Well, first thing is we need to deal with this probability into a z-score into an x. So what we are looking at is we're going to look at some standard normal distribution, right? This is the standard normal. We're going to look at the standard normal distribution, and we're going to say, hey, we're looking for values that are smaller than our border value, because this is the border value, right? So this is border. Right? So we're looking for some value, probability of some value being smaller than a border value, and the probability of that being 93%. Well, 93% means most of the graphs. So questions, is this on the left or on the right? This is on the right. So this is going to be here. Right? So our star is going to be on this, and we're going to be looking at all this. But because we want to attach probability to it, this cannot be x, this has to be z star. Alright, so let's look up. And 0.9332. 0.9332. Oh, look, it's right here. Lucky us. So 0.9332 is right here. And that gives us 1.5. Not x star, but z. It gives us the z-score, right? It's right here. So this is 1.5. And that's our z-star. So now we calculate our border value. Our border value equals the population mean plus border z-score, which is right here, times standard deviation. So our border value equals to 10 plus 1.5 times 2.5. And that comes out to be, that's 3.75, so that's 13.75. And this number is this number. All right, example 16. Find x star, so and it should say that this, yep, that's normally distributed, otherwise we won't be able to do stuff with it. Alright, so our border value is smaller than our x, right? So border value is on the left, and starting from this side all the way to the border value is 65%. It's 50 to the line, so it has to be somewhere below the line. And there's our star position. In our case that's going to be the z star. So if this is 65, this is going to be 35. We're looking for this. This is 35, which means that we're going to be looking up z of 0.35. So 0.35. I got negative 0.39 or thereabout. Let me show you. Point 0.35, 0.35, 0.35, 0.3, lower, here, between those two. This is 20 away, this is 17 away, this is closer. And that's negative 0.3, and then this column is for 9. Right, this is 9.39. It's right here. So this is how I got this equal to 0.39, which means that our border value equals to 175 plus minus 0.39 times 12. Which comes out to be 175 minus 0.39 times 12, which comes out to be 170.32. That's our x star. X star. All right, that's 17. Oh, cool! I have 2 pages, 3 pages left. All right, so this is example 17. Mean 510, standard deviation of 60. Are you guys still awake? We've been at it for a little bit over 2 hours. Maybe we should make another joke. That mosquito. All right. You know what? Screw it. Let's keep fighting. So standard normal scores, mean, standard deviation. A selective university decides to give serious consideration for admission to applicants whose scores are in the top 5%. And this is the whole English to math part. This is one has to be careful what this means. find the minimum score that meets the, so we're looking for minimum score. So top 5% means right here, right? 5%. If this is 5%, then means the rest of it is 95%. And so what we're looking for is we're looking for this right here, this z-score. So what we're looking for is probability that x is greater than x bar is equal to 0.05. That's the minimum score. That's the border, right? Minimum score. That's the border value. So all our other scores have to be above, and all of our other scores have to comprise the top 5%. So this is what we're looking for. So what we need to find is z of 0.95. We need to find the z. 95%. Oh, I get between two scores. So let's pull this up. So we're looking at 95. 95 is right here. Somewhere between those two numbers. Right here on the bottom middle. And because 95% is something we're going to use a lot, a good rule of thumb is to approach it with an extra decimal place. So what we are looking for here is it's going to be 1.64 or 1.645. Sorry, 1.65. So what we do for 95% in most cases is we're going to say it's 9.645. There's only two numbers we round up in average into the middle, and this is one of them. 1.645, and then of course the negative equivalent of it. And so now we look at the x star, and what do we get? Well, we get that 510 plus 1.645 times 60, right? And that comes out to be 608.7. So anybody that scored 608.7 or higher is in the top 5%, and they should be considered. Right. The difficult part of this problem is this. What does this mean? What does this mean? And how do you get this? Because once you have this, the rest of it is follows. The difficulty part is getting the English into the math. And once you have that, that goes. And then the difficult part is to say what this means. Well, this means this is the all scores of 608 or higher are top 5%. English to math. The actual math is not very difficult, as I promised. And then math to English. That's all statistics is at this level. This is the difficult part. Doing this and then doing that. Because this, honestly, we all can do this, because this formula is not exactly screaming, I'm losing sleep at night. Alright. And example 18. All boys at a military school must run a fixed course as fast as they can. As part of a physical examination, finish times are normally distributed with a mean of 29, standard deviation of 2. The middle is 75. 75% of all finishing times are qualified as average. Well, sounds like my PE in high school. Find the range of times that are average. Okay. So somewhere here in the middle, there's 75. Well, there's two tails to it, right? There's going to be something above it. So if we go 1 minus 0.75, we get that these two pieces, this area and this area, right? So 75 plus 2 c's equals to 1, right? Because this whole thing has to be equal to 1. So how big is c? Well, 2c equals to 1 minus 0.75, which means that 2c equals to 0.25, which means that c equals to 0.125. Which means that the z-score here, right, the star z-score, is really the z-score responsible for cutting off 12.5%. And if we look up this for this area right here, we get that probability that z is smaller than z star, right, this area right here, equals 0.125, which means that z star has to be, well, let's take a look. 125, 125, 125, 125. I got 1251 at negative 1.15. Let's see if we can find it together. So we're looking at 12.5%, which means we're probably looking at here 0.1212. Oh, here it is, 125. It's right here in the middle. I'm going to zoom out, and 125 is negative 1.15. All right, so we have one of them. So what's the other one? Well, the other one is the same thing. So the two z-scores I'm looking at is this Now, if you write this, there's a mistake in it. Those two things cannot be equal to the same thing. So what we do is we just say minus. Right, that's the negative z-score, that's the positive z-score. That's the negative z-score. So that's the way to fix it. Alright, so now we have to do two calculations. One is x star equals to mu plus z star sigma. So the first x star is 29 minus 1.15 times 2, and the other x star is 29 plus 1.15 times 2. So the first one comes out to be 26.7, and the second one comes out to be 31.3. And so what's average? Average is between 26.7 and 31.3 minutes. That's the middle 75%. Oh, look at that, they changed it into seconds. Ooh, fancy. Screw them. We're not doing that. We have important things to do with our lives. And ladies and gentlemen, that finishes chapter 5 for examples. So let me know if you have any questions. I think most of it is relatively straightforward. If you survive chapter 3 and 4, this should have been a learning experience, but not terribly difficult. And I'm going to start working on chapter 6 because we are starting to slowly run out of time to be miserable with statistics, because this class is almost over. So just let me know and whatnot, and I will see you on Piazza. Thank you for hanging out, and now I'm going to get some ribs. I'm really starving. Have a good evening.